Okay, elastic collisions in one dimension. So this is getting into more specific subcases of that general conservation of momentum. So the key difference with elastic collisions is that the kinetic energy is conserved. So the kinetic energy of each colliding body may change in an elastic collision, but the total kinetic energy of the system does not change. So for a stationary target, again, this is assuming that your target's at rest. This is a little bit more specific than I would tend to be. But we have our total initial momentum is equal to our total final momentum, where in the initial momentum, they've set V2I equal to 0, so that term disappears. And similarly, because it's an elastic collision, we can set our kinetic energy initial equal to our kinetic energy final. This is what we did in lab when we looked at some elastic collisions. Only difference here is not, in some cases you had the target at rest, but in other cases the target had an initial velocity. In those cases you would need to add that extra 1/2 m2 v2I squared to this left side of the equation. Now with some algebra, which it's a little bit painful of algebra, so I don't recommend doing it. I recommend taking their word for it. For this particular scenario of having a stationary target, you can show that the final velocity of one object is equal to the difference in masses divided by the total mass times the initial velocity of that same object. And similarly, the final velocity of object 2 is equal to 2 times the mass of the first divided by the total mass times the initial velocity of 1. There's no term for the initial velocity of 2 because that's 0, because we're assuming that's a stationary target. So this is a useful result that you can take if it meets the right scenarios to use this equation. And we can test this out for a few different scenarios, right? One is we could test it out if m1 is equal to m2, if we have equal masses. If they are in fact equal, then notice m1 minus m2 is going to become 0. So our final velocity of particle 1 is going to be 0 as well. First object's going to stop. For the second object, if all of these m's become the same thing, then we have 2m divided by 2m, and that cancels. So our final velocity of the second is just equal to the initial velocity of the first. It's a perfect transfer from one to the other, much like Newton's cradle. So that's an interesting special case. It matches what we've seen in our everyday life. We also could look if we have a massive target, right? Where if we have something like something small coming in to hit a bowling ball, right? Well, in that case, what you'd expect is that the ping pong ball is going to just bounce off the bowling ball. And we can double check that here, right? If m2 becomes really, really large, then v2 final of the massive target is going to be m1, which is 2m1, which is pretty small, over a really, really large denominator. So v2f is just going to be basically 0. For the final velocity of 1, the ping pong ball for our analogy there, we have basically m2 dominating over this m1, so it ends up being negative m2 over m2 times v1I. So our final velocity of particle 1 is equal to the initial velocity with the opposite direction, the negative sign. Remember, with momentum, the direction does matter. So you do want to put in a positive or negative sign depending on the direction that it is going. You also could have a massive projectile where m1 is much, much bigger than m2. And in that case, as we check this equation, right, our m2s would sort of disappear, and we'd be left with the final velocity of 1 of this projectile is equal to m1 over m1, basically 1 times v1I. Basically, if the bowling ball comes in to hit the ping pong ball, the bowling ball is going to keep going, right? It's not going to stop. Now, for the small target, though, like the ping pong ball or tennis ball, we now have 2 times m1, this big, big m1, over basically m1. m2 basically disappears in comparison. So v2f, the final velocity of the target, becomes twice as big as the initial velocity of the projectile. It can shoot off, and there's a great video of this. I'll post a link to it, but you can also get to it from the slides, of showing how if you stack balls, like a basketball with a super ball on top, they won't just bounce together. You'll be able to see this effect, and the ball on top of the basketball will shoot upward. You have to be careful if you try this at home. Make sure you are not standing directly above it. But I do encourage you to check it out. All right, now for a target that's also moving, this is the most general set of two equations for an elastic collision, right? So it has to be an elastic collision still. But now we have a target that also has some initial velocity. And the first half of the equations is almost the same. It is exactly the same. We've just now added a second term to each of them that's based on this v2I, right? There's some initial velocity of particle 2. So as long as the problem mentions that's an elastic collision, this is a really quick way to start with the initial velocities and the masses and figure out how fast they're moving after they collide. So those are two handy equations to keep in your back pocket for any time a problem mentions it's an elastic collision. That's where we'll wrap up. The very last section will be looking at collisions in 2 dimensions coming up soon.